Good morning, everyone. So today, we're going to talk about the last two types of chemical reaction, which are the single replacement reaction and the double displacement reaction. First of all, our topic for today is divided into two parts. First, the things we need to know about the single replacement and double replacement, and second, we need to know how to predict products and how to balance these reactions.
Replacement reaction. What is replacement reaction? Well, a replacement reaction occurs when elements switch places in compounds. This type of reaction involves ions, the electrically charged versions of atoms, and ionic compounds. Generally, a more reactive element replaces an element that is less reactive. The less reactive element is set free from the compound. The replacement reaction has two types. It has the single replacement reaction and the double replacement reaction. So first, let's discuss about the single displacement. With a general pattern of AB plus C is equals to AC plus B. So, in the single displacement reaction, the following contents that we're going to discuss is about its definition, pattern, concept, and how to predict the product and balance. Single replacement reaction. A single replacement reaction is sometimes called a single displacement reaction. It is a reaction in which one element is substituted for another element in a compound. The starting materials are always pure elements, such as pure zinc, metal, or hydrogen gas, plus an aqueous compound. When a replacement reaction occurs, a new aqueous compound and a different pure element will be generated as products. When you look at the chemical equation for a reaction, a single displacement reaction is characterized by one cation or an ion trading places with another to form a new product. The general pattern of a single replacement reaction is shown below. The AB plus C is equals to AC plus B, where the single anion replaces an ion in a compound, or the A plus BC is equals to B plus AC, where a single cation replaces cation in a compound. From the general pattern A plus BC is equals to B plus AC, where in this equation, usually for cation replacing cation in a compound, A represents a more reactive element and BC represents the original compound. During the reaction, A replaces B, forming the product compound AC and releasing the less reactive element B. As an example, the magnesium plus iron trioxide is equals to iron plus magnesium oxide. As you can see, magnesium or the cation replaces iron, another cation, and form a new product. AB plus C is equals to AC plus B. In this equation, usually for an ion replacing an ion in a compound, AB represents the original compound, and C represents a more reactive element. During the reaction, C replaces B, forming the product compound AC, and releasing the less reactive element B. As an example, sodium chloride plus difluorine is equals to sodium fluoride plus dichlorine. As you can see, fluorine, an ion, replaced chlorine, another anion, and form a new product. Reactivity series or activity series ranks elements in order of their reactivity for certain types of reactions, including single replacement reactions. The more reactive elements will replace the less reactive elements in the reactivity series, but not the other way around. There are separate rankings for elements that form cations and elements that forms anions. As an example, we can say that in the equation, aluminum replaced copper, because it is more reactive based on the reactivity series. The higher the element's position in the column, the more reactive it will be. For more reactive elements, we will place less reactive elements in a compound.
After knowing the definition and all the concepts about single displacement reaction, including the reactivity series, now, how do we predict the product of a single displacement? Information was already tackled beforehand, and in this part, we are now going to specifically state the steps on how to get it. So, how to predict product of a single displacement or replacement reaction? A single replacement or displacement reaction replaces one element for another in a compound. The periodic table or an activity series can help predict whether single replacement will occur or not. For example, let us predict the product of magnesium plus iron 3 oxide. Note that the following examples aren't balanced yet. So, these are the following steps on how can we predict products of a single displacement reaction. First, to predict the product, we need to use the reactivity series or activity series table to determine if a reaction occurs or not. Second, we're going to look at the metal from left to right. So in this case, we are going from magnesium to iron. Third, note that if the first metal, which in this case is magnesium, is higher than the second metal, which in here we have iron, then a reaction will occur. Basically, we are going from left to right. So, if the metal from the left is higher than the metal from the right, then a reaction will occur. And fourth, we'll now switch the metals to form a new product by the use of the pattern A plus BC to B plus AC. Why are we going to use this pattern? Because as we know, magnesium plus iron oxide are both have cations. So we're going to use the pattern which have cations. So the next step is we're going to copy the pattern or we're going to use the pattern. So as you can see, we moved the iron from left to right. The iron now is an element and not a part of a compound. And for the second element or the compound, we have magnesium plus oxygen. So why did magnesium comes first before oxygen? Because positively charged metals go first before negatively charged nonmetals. Note that 2 and 3 subscripts of iron and oxygen in the left are only there to balance the charges of iron and oxygen. So in this part, we need to refer to our predict tables. So they will not be copied when we are predicting the new product. Instead, look at magnesium and oxygen's charges. Magnesium has a +2 charge, while oxygen has a -2 charge. So we don't need to put it in the new formed compound because they are both 2 and we can divide it by itself or by 2. So basically it will be magnesium 1 and oxygen 1. Or we can rewrite it as magnesium and oxygen only. So now we have predicted the product. So magnesium plus iron 3 oxide to iron plus magnesium oxide. The next step here is to balance this. But then, that is for the second topic. So we're going to stop here and find more examples to predict products. So for our next example, we have silver plus potassium nitrate or Ag plus KNO3. To predict the product, first we need to use the reactivity series table to determine if a reaction occurs. So as like the first example, we're going to look at the metal from left to right. So in this case, we're going from silver to potassium. Remember that if the metal from the left is higher than the metal from the right, so a reaction will occur. But if the metal from the left is lower than the metal from the right, so there will be no reaction. So in this case, we have silver, which is from the third to the last of the table, and we have potassium, which is at the top of the table. So basically, potassium is higher than silver. In this case, Silver is lower than potassium, so there will be no reaction that will occur. So for our third example, we're going to deal with an ions or the negatively charged ions. So in our example, we have sodium chloride plus chlorine gas. In this case, we're going to use the pattern for an ions, which is AB plus C to AC plus B, since we're dealing with replacing an ion to another anion. To predict the product, first, we need to use the activity series table for an ion to determine if a reaction will occur. Next, let's refer to the reactivity series of an ion to show if it can be replaced. In this example, we have fluorine is higher than chlorine, so we need to replace it and form a new product by following the pattern. And now we have sodium chloride plus fluorine gas to sodium fluoride plus chlorine gas. So before we proceed in balancing single displacement reactions, as you can see, fluorine has a subscript of 2 in the left, and chlorine also has a subscript of 2 in the right. So why is it? It is because they are called diatomic elements. Diatomic elements include hydrogen, nitrogen, oxygen, fluorine, chlorine, and iodine. Diatomic elements must be written with a subscript of 2 when they are alone. And for our last subtopic for single displacement reaction, we're now going to learn how to balance this reaction. How to balance single displacement reaction? You balance the equation for a single replacement reaction the same way as any other equation. You place coefficients. What are coefficients? Coefficients are numbers like 1, 2, 3 in front of the chemical formulas so that the numbers of atoms of the elements are the same on both sides. So for example, we have Al plus CuSO4 to Al2SO43 plus Cu, or aluminum plus copper 2 sulfate to aluminum sulfate plus copper. So we need to follow these simple steps. First, if you look on the left side of the equation, which is the aluminum plus copper 2 sulfate, there is only one sulfate ion, which is SO4. SO4 is the sulfate ion. And on the right side, there are three sulfate ions, which is the SO4 3. So we need to place a coefficient of 3 in front of the CuSO4 to balance the equation. That's the first step. After putting a coefficient of 3, we'll now have Al plus 3 CuSO4 to Al2 SO43 plus Cu. So we already balanced the sulfate ion. Now, the aluminum needs to be balanced. There are two aluminum atoms on the right side of the equation and only one on the left. So we need to place a coefficient of 2 in front of the aluminum on the left side. And we'll now have 2Al plus 3CuSO4 to Al2SO43 plus Cu. Lastly, we need to balance the copper or the Cu. There are three copper atoms on the left side and only one on the right. So what do we need to do? We need to place a coefficient of 3 in front of the copper on the right side so they will be balanced. So eventually we will have 2Al plus 3 CuSO4 to Al2SO43 plus 3 Cu. Now the equation is balanced. There are equal numbers of atoms of each element on both sides and equal numbers of polyatomic ions on both sides. So we'll need to check. First, we need to see aluminum. How many number of aluminum can you see on the left side? As you can see, there are two aluminum on the left side. How about on the right side? We also have two aluminum. Next, we need to see for the copper. The left side, we have three coppers. As you can see, there's 3 Cu. And on the right side, we also have 3 Cu, so they are also balanced. Lastly, we need to focus on our sulfate ion. On the left side, we have SO4, but then we have a coefficient of 3. So we also have 3 sulfate ions. And on the right side, we have SO43, which also have 3 sulfate ions. So they are also balanced. And now, The final balancing of this problem is 2Al plus 3CuSO4 to Al2SO4 plus 3Cu. So at this point, we are now done with single replacement or displacement reaction. We already know its definition, concept, its pattern, on how to predict its product, and how to balance its equation. At this point, we're now going to talk about the double displacement reaction.
So now, we were going to know what does a double displacement reaction really means. And by looking by its title, our mind starts to guess and pop some questions. What does the double displacement reaction really means? And how does this affect in the field of the chemistry? And also, how does this reaction can be predicted? And how can this be known by its formula? First, here's a quick definition. A double displacement reaction is a type of chemical reaction in which the reactant ions exchange places to form new products. Usually, a double displacement reaction results in a precipitate formation. The chemical bonds between the reactants may be either covalent or ionic. It is also been said that double displacement reaction takes place mostly in aqueous solutions, wherein the ions precipitate and exchange of ions takes place. For example, when a solution of barium chloride is mixed with a sodium sulfate, a white precipitate of barium sulfate is formed rapidly. Then these reactions are ionic in nature. And to know if there's any other names with double displacement reactions, there is another name of double displacement reactions wherein double displacement reactions are referred to by a series of other names including displacement reactions, double displacements, metathesis, solution reactions, or ion reactions. These terms refer to a specific type of reaction that occurs between two ionic compounds. And now that we're familiar with the double displacement reactions by its leading definitions, we're going to know what is on how or how does this double displacement reaction formulates by knowing its formulas. So the general pattern of a double displacement reaction is shown below, whereas AB plus CD is equal to AD plus CB. In this type of reaction, the positive charge cations and the negative charge anions of the reactants both trade places, whereas double displacement takes place to form two new products. We all know that a double displacement reaction exchanges the cations or the anions of the two ionic compounds. A precipitation reaction is a double displacement reaction in which one product is a solid precipitate. Solubility rules are used to predict whether some double displacement reaction will occur. And now, where AB exists as A positive and B negative ions in solution and CD exists as C positive and D negative ions in solution. As the ions came in contact with each other, there are 6 possible combinations that might conceivably cause a chemical reaction, wherein 2 of these combinations are the mating of ions of like charge, that is A positive plus C positive and B negative plus D negative. But since like charges repel, no reaction will occur with these combinations. 2 other possibility combinations are those of the original compound, that is A positive plus B negative and C positive plus D negative. Since we originally had a solution containing each of these pairs of ions, they can mutually exist in the same solution. Therefore, they do not recombine. Thus, the 2 possibilities for the chemical reaction are the combination of each of the positive ions with a negative ion of the other compound. That is, A positive plus D negative and C positive plus B negative. Wherein an example of an overall equation for a double displacement reaction can be seen below.
In this slide, I will explain to you on how to predict product of double displacement. So first, identify which elements would be likely to swap. According to its definition, double displacement reaction occurs when parts of two ionic compounds are exchanged, making two new compounds. So in the double displacement reaction, it will only occur in ionic compounds. So these ionic compounds consist of positively and negatively charged ions. So these ionic compounds are exchanged, making two new compounds. So these two new compounds are the product of double displacement reaction. It is also a combination of metals and non-metals. So the overall pattern of a double replacement reaction looks like this. So as you can see, all of the pattern of a double replacement reaction is ionic compounds. And as you observe, only the negatively charged are exchanged. So this is the reactants and these are the product of double displacement reaction. So B negative is exchanged with D negative in the product. D negative is exchanged in B negative in the product. So again, as you observe, only the negative charge are exchanged in the what we call the product of double displacement. So number 2, not all double replacement reactions will occur. So not all the ionic compounds will be applied in double replacement reaction. I will explain further to you on the next slide. So in order for a double replacement reaction to take place, both of the reactants must be soluble in water. If a compound contains at least one of the ions that is proven soluble, then the compound will be at least moderately soluble. So reactants should be both soluble in water. Number 4, one product must be soluble and one product must be insoluble. The insoluble product is the precipitate that forms when the reaction takes place. Usually, a precipitate is a solid, but it doesn't have to be. So, the product of double displacement, one product should be soluble and one product should be insoluble. So again, both of the reactants should be soluble in water and product must result to one product must be soluble and one product must be insoluble. So that's the other way to predict product of double displacement. So I have here solubility rules for double replacement reactions. Compound, salts of alkali metals and ammonia, these are soluble. Exceptions, none. Nitrate salts and chlorate salts, these are soluble. Exceptions, none. Sulfate salts, these are soluble. Exceptions are lead, silver, mercury, barium, strontium, and calcium. Chloride, bromide, and iodide salts are soluble. Exceptions, silver, mercury, and lead. Carbonates, phosphates, chromates, sulfides, and hydroxides. These are insoluble. Exceptions, compounds of the alkali metals and of ammonia. So I have also here a solubility chart. So this chart will help us to determine the reactants and the product if they are soluble or insoluble. Solubility chart is a chart with a list of ions and how, when mixed with other ions, they can become precipitates or remain aqueous. S stands for soluble in water, A stands for soluble in acids, B stands for partially soluble in water, I stands for insoluble in acids and water, small letter A, slightly soluble in acids, insoluble in water, and the small letter D, decomposes in water. So I have here an example. So let's try and predict this example. So 2KOH or potassium hydroxide plus lead nitrate is the reactant, and its product is 2KNO3 or potassium nitrate plus PbOH2 or lead hydroxide. So as you can see, only the OH and NO3 too is exchanged. OH is transferred here and NO3 too is transferred here. So in predicting a product of double displacement, again, we need to check if the reactants are both soluble and if the product is soluble and insoluble. So let's use the solubility table. So let's check the potassium and hydroxide. So here, potassium and hydroxide. So as you can see, it is soluble in water. So 2KOH or potassium hydroxide is soluble. So let's check this potassium nitrate. Potassium nitrate. So as you can see, potassium nitrate is soluble. So using a solubility table, both reactants are soluble, so reaction occurs. So when we confirmed that both of the reactants are soluble, then we can now apply the double displacement reaction. So the double displacement reaction is applied. As you can see, the OH is transferred and the NO3 too is transferred. So this is potassium nitrate and this is lead hydroxide. So let's check it if this one is soluble and if this one is insoluble. So potassium nitrate, let's check it first. Potassium nitrate. So as you can see, it is soluble. So check, this is a soluble. So let's check the lead hydroxide. Lead hydroxide. So as you can see, it is not soluble but partially soluble in water. Partially soluble in water. So it is considered as a insoluble. Using a solubility table, potassium nitrate is soluble, lead hydroxide is insoluble, so reaction occurs. So for the recap, double displacement reaction will likely occur in ionic compounds. So it is also a combination of metals and non-metals. So in double displacement reaction, there is a pattern to be followed to have a product of double displacement reaction. So again, both reactants should be soluble so that reaction will occur, and the product, one must be soluble and one must be insoluble. So this is how we predict double displacement reaction. So in the next slide, Nikos will explain to you on how to balance double displacement reaction.
How to balance double displacement reaction. When the chemical formula for each ionic compounds is written correctly, you can balance the equation like any other chemical equations by making sure the number of atoms for each element is the same on the left and the right. To illustrate, let us look at the first example of double displacement reaction. we have NaOH plus FeCl2 to form FeOH2 plus NaCl. As we observe, the groups of ions are the following: the Na, OH, Fe, and Cl. To balance this, we need to count all the numbers that each ions contains in each sides. To illustrate, as you can see at the presentation, we have one Na from the left and one Na from the right. We also have one OH from the left and two OH from the right. Next, we have one Fe ion from the left side and one Fe from the right. Lastly, we have two Cl from the left and one Cl from the right. As we look at the presentation, we can observe that the OH and Cl are not equal, which means they are not balanced yet, and we need to balance them. To make that, we need to put 2 before NaOH at the left side and 2 before NaCl at the right side. And final reaction would be 2 NaOH plus FeCl2 to form FeOH2 plus 2 NaCl. To illustrate the final balancing, we have 2 Na at the left side, which is equal to 2 Na at the right side. We also have 2 OH both left and right side, and they are equal. Next, we have 1 Fe from the left and 1 Fe at the right side. Lastly, we have 2 Cl at the left and 2 at the right. To conclude, all the elements, both sides are equal, and that's how we balance a double displacement reaction. Now, we do have another example. Let's balance this one. We have silver nitrate, and the formula for that is AgNO3, and another compound, which is potassium chromate, which is the formula of K2CrO4. To form silver chromate, which is Ag2CrO4, plus potassium nitrate, which is KNO3. Next, we need to count all the numbers that each elements do have. First, we have 1 Ag at the left and 1 Ag at the right. Next, we have 1 NO at the left and 1 NO at the right side. Then, 2 K at the left and 1 K at the right side. Lastly, we do have 1 chromate at the left and 1 chromate at the right side. As we can observe, the presentation, the Ag and K are not balanced. With that, we need to place 2 in front of silver nitrate on the left side and 2 in front of potassium nitrate on the right side. Therefore, the final balancing and reaction is as follows. We have 2AgNO3 plus K2CrO4 and 2 KNO3 plus AgCrO4. With that, the balancing would be illustrated below. We have 2 Ag on the both sides, left and right. We also have 2 NO3 on the left and 2 at the right side. Next, we have 2K both left and right sides. Lastly, we do have 1 chromate on the left and 1 chromate at the right. In conclusion, they are now balanced, and this is an example of double displacement reaction. I believe we understand how to balance a double displacement reaction, and at this point of time, for us to have a deeper understanding on balancing double displacement reaction, we have provided another example on how to balance it. For our last example, let us look at the reaction between NaOH and BaBr2. For this reaction, OH is a polyatomic ion and is treated as one whole anion. The individual ions and the charges for these two reactants are demonstrated below. We have the cation, which is Na, and anion, which is OH, and another cation, which is Ca, and anion, which is Br. At this time, we can switch the ions as we can see at the presentation. It would go as NaOH plus CaBr2 and the Na is being combined to Br2 to form NaBr2. At the right side, we have Ca that is being combined to OH to form compound of CaOH2 at the right side. Let us now count all the numbers that they contains for us to know if it is balanced or need to be balanced. We have 1 Na from the left side and 1 Na from the right side. We also have 1 OH from the left and 2 OH from the right side. Next, we have 1 Ca from the left and right side. Lastly, we have 2 Br from the left and 1 Br from the right side. As we can see at the presentation, the OH and Br from both sides are not balanced. To balance them, we need to place 2 before the NaOH and 2 before NaBr to make them balanced. And the final reaction would be 2 NaOH plus CaBr2 to form 2 NaBr plus CaOH2. Let us see if they are now balanced at the presentation. We do have 2 Na from both sides. We have 2 OH from both sides. Another 1 Na from both sides, left and right. And 2 Br from left and 2 Br from right side. Therefore, they are now balanced, and this is an example of double displacement reaction.